We shall continue our study of asymptotic analysis of algorithms. And today, after having seen growth functions, the order notation, the upper bound, the lower bound notations, we will now try and analyze some of the algorithms or programs that we have written till now and see what this analysis means, and also study some of the techniques of analyzing or trying to find out these asymptotic growth functions. So we'll pick up quickly these problems: the maximum of n numbers, the exchange sort, the tournament sort, Fibonacci numbers, the merge sort, and the quick sort. These are the ones we have done. We've also done towers of Hanoi, permutations, the stamps problem, which we shall come to them when the time permits. The maximum of n numbers was something which we did in the previous class, and without writing the routine again, we found out that Fn is of the form A n plus b, and we can say this is order n. Just before we continue with this, if Fn is equal to k, which is a constant, then it is said to be order 1. This constant is usually called order 1. It is the same as order 0, order 3, order 4, order 5. All of them mean the same thing. But the language which we use is constant complexity is order n. When we say order 1, when we say order n, we say it is a linear time algorithm. Now, if a function is varying with n and you have to read all the inputs, anyway it cannot be better than linear time. But is the constant minimum is something we can analyze a bit later on, but presently we are only bothered about asymptotic analysis. So finding the maximum, finding the minimum, all of them are linear time. And you really cannot find the maximum of n numbers in less than linear time. So that part is over. If it is unsorted, if it is sorted, then obviously you can find it in constant time. If it is already sorted, and you know finding maximum of n numbers is obviously constant time. But an unsorted arbitrary list of n numbers, finding out the maximum is the best possible order that you can get asymptotically. The order is linear. So the next one which we will come to is the exchange sort. The exchange sort, the core part of it, there are two loops. For I equal to 1, I less than n, or if you wrote 0, then you would have written n minus 1. For j equal to I plus 1 to j equal to n, that is less than n, j plus plus. If data I is less than data j, then this is what you do. So if you make a quick analysis, then this part will be executed once, this will be executed n times, this will be executed once, n times, this will be executed n times, this is in a loop, this will be executed n into n minus 1, whatever, this similarly, and the inner loop will be executed in what order of complex. You can find the exact, you can put 1, 1, 1, 1 and find the exact value. But if you have got the hang of order of analysis, you can say it will be of the type of an square plus bn plus c. Very quickly you can say it is going to be of this type, though the constants will be dependent on what you do. And you can say that exchange sort is order n square algorithm. So this is an order n square algorithm. Is that okay? let us come to this tournament. You remember this diagram of a tournament in which we found out we had these n numbers and we used an array of size 2n minus 1 and we compared 2 and put in the index of the half place. So building up this tournament, we did it in a loop from back, compared these two, 14 and 15 and put it in 7, 6 and 9 and put it in 9, 15 and 1 and put it in 5, 8 and 9 and put it in 4 here, and this is what we did. So this loop is of order n. If this is 2n minus 1, this will be approximately proportional to 2n minus 1. So building up the tournament is of order n time. So tournament build if you do not understand, please stop me. Tournament build is order n. Find out the maximum element is constant time after tournament build. Get next max. What did we do? We went along the maximum, and if we assume the minimum, then you make it less than the minimum, and then you go up. Now, how many comparisons do you make when you go down? Log n. And when you go up, log n. So to get the next max, you make 2 log n. 2 log n. So next max and if you repeat this next max continuously, then you will require some, this is Fn, isn't it, which is An plus B, find max, next max. This is what you will continuously do, plus n into, this was of the form A log n, plus any terms which are less, linear time terms, etc., etc. Bn plus whatever it may contain. So this term will be of A, this is A1, say this is A, this is A dash, this is B dash. So this whole term, very quickly you can see that the highest order term will be An log n. Huh?
B dash n.
No, B dash n is not here, sorry. B dash. Maybe some constant time may be required. This is not n, sorry. Then this would have been n, order n, because log n is more than. So this, the whole sorting of n numbers will be done in order n log n time, which is much better. So now let us see. One we have got Fn is equal to n square. The other we have got Gn, which is equal to n log n. These are the two order functions. Now clearly Gn is upper bounded by Fn, and Gn is not lower bounded by Fn, that these two are not of the same order. Therefore this is much better than this. There are various other issues relating to orders, especially when you consider complexities of the type n to the power, say, log n. How does it compare with n to the power 500? How will you compare these two? Take the logs on both sides and compare, you will get a comparison between both of them. If you cannot directly compare these two, take log on both sides and compare. This will be better than this. See, this one, its growth is a polynomial, where this growth, this log n, will increase with n. So this one will grow faster than this one. So between these two algorithms, this will be better than this. In fact, for any constant n to the power k, for any fixed constant, maybe even 2 million, it will be better than this in order terms. So we have got this tournament sort is order n log n algorithm, therefore it is more efficient in asymptotic worst case complexity than a exchange sort. But if you take 100 elements, maybe you just don't know, because the constants may be very big here. Let us come to the Fibonacci number problem. And here we come, in the previous two cases, we had very simple loops which we could analyze. In the Fibonacci number problem, how will we find out what is the complexity of this? Can anybody have any suggestions? What is the complexity of this? If n is equal to 0, then it is one check, constant time. It is constant time. If n is equal to 1, it is constant time. Otherwise what? So we have been able to say for Fibonacci numbers, Fn is equal to, let us write it out like this. If n is equal to 0 or 1, then Fn is equal to constant k. Is order 1. Else, what? It is the time to do this plus the time to do this plus another constant, which is say 1. So now the complexity equation again becomes a recursion. And the complexity equation, the time n for Fibonacci is equal to, let us say constant, we can make it 1. We are doing asymptotic analysis. For n less than equal to 1, and is equal to t of n minus 1 plus t of n minus 2 plus 1 for n greater than 1. We have not found the solution. We don't know the order yet. This is what we have. Now, can you tell me what order this is? This is called a recurrence relation or a recurrence equation. This one can be solved. Do you know the answer to this one? Can you solve it in terms of Fibonacci n? See, it looks very similar to Fibonacci numbers itself. By the way, do you know what is the value of Fib n? 1 by root 5 n 1 minus 1 by root 5 to the power n plus 1 plus 1 by root 5 to the power n, the whole 1 by 2 root 5 or something like that. It is like this, something like, it's called a golden number. But this Tn can be written in terms of Fib n, you know. Can you make a guess? Is Tn equal to fib n? Just what is Tn? Tn is equal to 1 fib n plus 1. Is it equal to fib n plus 1? How will you prove this? Yes or no? How will you prove it? Substitute here by induction. Fib n plus 1. So this will be Tn. If Tn is fib n plus 1, then this by induction must be fib of n plus fib of n minus 1 plus 1, which will be fib of n plus 1 plus 1, which is not true. Now looking at this, can you make an adjustment? Put fib n plus 1 minus 1. Then you will get one minus 1 here. You will get one minus 1 here. And you will get one minus 1 here. Right? Tn is equal to fib of n plus 1 or not. This is not true. Why? If it were true, by induction, this would have happened. Tn is Tn minus 1. So by induction, this should have been fib of n plus fib of n minus 1 plus 1. Now fib of n plus fib of n minus 1 is fib of n plus 1. So you will get fib of n plus 1 plus 1, which is not true. But if you put it just 1 minus 1 here, you will get a minus 1 here, you will get a minus 1 here, you will get a minus 2 here, and this will give you fib of n minus 1. So even if you don't know this, you can say Tn this much you can say. Isn't it? Now fib of n plus 1 is an exponential number. Just see. So Tn will be, you can always write, at least it will be upper bounded by 2 to the power n. It will also be lower bounded by 2 to the power n. You can show that. I just leave it to you to try out, because these are both numbers which will be exponential. The growth of this will be exponential. So this algorithm is of order exponential time, 2 to the power n. It grows very rapidly compared to an algorithm like n square or n cube, which grows as a polynomial function of n. We have to see what we can do about this. But the one point that we get from analyzing recursive equations is that these recursive definitions, the complexities of these recursive definitions can be found by solving certain recurrence equations. Is that idea clear? That the solutions to recursive definitions, or the complexity, time complexity, asymptotic time complexity of recursive functions or inductive definitions, can be obtained by solving certain recurrence relations. And we've already got several such problems at our hand, and we'll see one of them. Let us see the merge sort problem. if you remember, the merge sort problem was if we split into two parts, equal parts or unequal parts or whatever. So split into two parts and then sort individually and then merge the two sorted lists. And we did not decide on where to split, right? We did not decide on where to split. We said we'll decide later on. Now is the time we'll see if we split in different ways, what we will get. Now first let us understand what this merge routine does. This merge routine, it takes in our final implementation in the same array a set of numbers, one pointer here, one pointer here, and in another array it compares these two. The smaller of the two, if you are sorting in that order, is written. Suppose this is 5 and this is 3, then 3 will be written and this pointer will move here, this index would move here. So for every number which is written here, at most one comparison is done. At most one comparison is done. So for finding out merging of m plus, say, m1 plus m2 numbers, so total of n numbers, if I have to merge, I have to do my complexity will be of the form like this, no more than this, because I do not have to do more than n comparisons and more than n such assignments here. That's all I have to do. So merging of n elements is order n time. So we know merging of n elements is order n time. So we come to merge sort. We are splitting into two parts. Now we could split 1 n minus 1, 2 n minus 2, 3 n minus 3, or we could split up half half, 3/4, 1/4, 1/10, 9/10. So suppose we split up into 1 and n minus 1. Then what will be our equation? Tn is equal to constant for n equal to 1. That is known. When there is one element, it is constant time. Otherwise, it is T1 plus Tn minus 1 plus merge time, which is order n. Order n you can write as n also, because it will not affect the order of the complexity, which is the same as Tn minus 1 plus n plus 1. So Tn is Tn minus 1 plus n plus 1, which is, if you start expanding out, how will you solve this? Can you solve this? Try it. Expand it. Tn minus 2 plus n minus 1 plus 1 plus n plus 1. This Tn minus 1 will break up as Tn minus 2 plus n minus 1 plus 1. Like Tn broke up as n minus 1 plus n plus 1. This will break up as n minus 2 plus n minus 1 plus 1. So it will be Tn minus 2 plus n plus n plus 1. The next step you can write in one shot, Tn minus 3 plus n minus 1 plus n plus 1. And this will go right up to T1 plus, when this is n minus 3, this starts from n minus 1. So when this is 1, which is equivalent to n minus 1, 1 is equivalent to n minus 1. It will start from n minus 3. If this is 3, this is 1. So if this is n minus 1, this is n minus 3, which is the same as 3. 3 plus 4 plus 5 plus n plus 1. So this will be T1 plus 3 plus 4 plus 5 or something like this, isn't it? Now this is a series summation which will sum up to order straight, right? Can you write the order term n square? So if you split up 1 n minus 1, 2 n minus 2, you are going to get an order n square algorithm. Alright. Let's see the, if you split up n minus 1, 1 also you are going to get the same thing. But suppose we split half up. Then our equation is Tn is equal to 1, n is equal to 1, and is equal to 2 of Tn by 2 for the two halves, n by 2 plus n by 2 plus n, right? So we have to solve this one. Let's start expanding. 2 of, expand Tn by 2, T n by 4 plus n by 2 plus n, which is the same as 2 square T n by 2 square plus n by 2 to the power 1 plus n by 2 to the power 0, right? This will come in, sorry, this will n. 2 into n by 2, this will be n. I'm sorry, this is not this. This part is okay. What is this part? N plus n. Right, this is it. This will be again broken up, 2 square, 2t n by 2 cube plus n by 2 square plus n plus n. This is 2 cubed t. If you stop me if you cannot follow. Now I can write the general term. Can anybody tell me the general term? 2k t n by 2k plus kn. Alright. So now what happens? When does this become 1? When n by 2k is equal to 1, which implies n is equal to 2k, which implies k is equal to log n to the base 2. At that point of time, this is 1, 2k is n, so this becomes n into 1 plus n log n. Which makes it order n log n. So now if we split half, we have got n log n. If we split 1 n minus 1, we get n square. So you remember what we were talking about in the initial class when we said that you leave that split alone. These are all the possible ways of designing. We'll analyze it and then we'll choose. Now you can check, if I split 3/4, 1/4, what will happen? Or you can write out an equation like this. I want, what is my choice of algorithm now? T1 is this. Otherwise, minimize this function. for whatever I. Find out the minimum value of I. Find out that value of I for which this is minimized. And solve this equation. And if you can solve this equation, you will get the optimal choice. This I may depend on n. It may say if n is 5, then you choose 2. If n is 7, you choose 3. If n is 9, you choose whatever it is. Or you may get a very simple solution like always choose I equal to n by 2. This may not lead to a very simple equation, simple solution, but this is what you have to do if you want to optimize your choice point. This is what is meant by the choice of that split. Is that clear? So we have now got an idea that in merge sort, if I split into two equal halves, I get an order n log n algorithm. So you will see all books of merge sort split into half. Because there is another proof that this minimizes. I equal to n by 2 minimizes it. But there are other proofs. If you write n by 4 and 3 n by 4, you will still get n log n. If you split it up in any fraction, you will get n log n. Half, you will get n log n. There are more details you can prove that if you split in half, you do less comparisons than you do when you split in 3/4, 1/4. That you can prove. But in terms of asymptotic complexity, we have reached this point in merge sort, saying that merge sort is best. We can prove, which I am not doing here. Merge sort is best when you split into half. Let us have a look at quick sort. Very similar. Quick sort equation is also very similar. Tn is equal to 1 for n is equal to 1 and is equal to, it depends on where your pivot element splits you. Now the pivot element you have chosen randomly. Alright. The pivot element is chosen randomly. So it can split you in 1 n minus 1. So in the worst case, quick sort can become order n square because choice of pivot element is not in your hands. But if you could choose the pivot element in such a way that it broke up the list into half-half, then you would have got order n log n algorithm. But then how will you find out how to split into half-half? That is, if you could split in linear time, look, you cannot take n squared time to split into half-half. That will spoil your whole complexity equation. So, given a set of elements, which is that element which splits it into half-half? The median. So, you have to find the median in linear time. If you could find the median of n elements in linear time, then you will choose the median and do quicksort based on that median. Then you would have got worst case order n log n time. But then how will you find the median in linear time? All of us find median by sorting. It's not a chicken and egg problem. There is a method to find the median in linear time, but that algorithm is slightly more complex. I will not go into it today, but you can find the median in linear time. So in the worst case, quicksort is order n square. In the best case, it is n log n, provided you can get it. Then you can start proving in the average case what happens and other things. We'll discuss it later on. But our tournament sort and merge sort, in the worst case, they are order n log n algorithms. And therefore, they are better in the worst case scenario than quicksort or exchange sort or bubble sort. But the merge sort has to be done by splitting half-half, not arbitrarily. So, asymptotic analysis helps you a lot, not only to find out how good your algorithm is, it helps you to decide on how to do a recursive decomposition and where to choose some of your choice points, which you may have left for the analysis part. It will also help you to understand which data structure is better and how to analyze the efficiency of your data structures, which we shall discuss later on. But this phase of understanding what is meant by complexity, what is meant by orders, how do we analyze complexity, how do we use recurrence equations, etc., will form the basis of the second phase, the last two parts of this course, mainly data structures, complete design of algorithms, as well as data structures, which we shall pick up in the final phase of this course.